For years, this sound has put many people on edge, as it foreshadows something we have come to dread, the sting of a bee. These yellow-winged creatures have been feared by people for many years now. Although tiny, bees can pack a whole lot of pain in their sharp stingers. However, as the world has progressed, scientists have found a way to not only extract but to utilize this pain-causing venom. This video will discuss what physically happens during a bee sting, the organic chemistry behind the chemical components of bee venom, as well as the uses of bee venom in modern-day science. Bee venom actually has many functions today, including its use as treatment for rheumatoid arthritis, multiple sclerosis, nerve pain, and many other diseases. This is due to the venom's anaphylactic property that allows it to break down cell membranes, increase the circulation of blood, and relieve the inflammation in joints. Now that you have a basic understanding of bee venom, let's see what the buzz is all about.
When a bee stings you, its sharp barbed stinger punctures the skin and injects venom. Contact with bee venom produces a waterfall of reactions in the human body. The venom is composed of over 60 identifiable components. The venom itself is water-soluble and must be injected into moist tissue in order to be effective. The actual composition of the venom injected is around 88% water and only 12% venom. The main component, making up around 50% of the dry weight, is a peptide called melittin. Melittin is composed of 26 different amino acids, making it a 26 peptide. 20 of those are hydrophobic and nonpolar, and the other 6 are cationic and very hydrophilic. The net charge of 6 actually becomes super important when we talk about what it does to red blood cells. A small amount of histamine is also found in bee venom. Many of the components in the venom can lead to histamine release by the body, which is prevalent during an allergic response and can cause itchiness and inflammation. The main allergen and most harmful component, making up 12% of the dry composition, is phospholipase A2. There are also acids present in the venom, including formic, hydrochloric, and orthophosphoric. Due to all the acid in bee venom, as well as melittin, which is a carboxylic acid derivative, the pH lands around 4.5 to 5.5. Since it is acidic, it's a pretty common myth that you can neutralize the sting site with a base. This would deprotonate the acid, making a carboxylate, or in some cases just the O-, and a protonated base. However, it's been shown that the acid actually does very little damage compared to the other components like melittin and phospholipase A2. The other reason why simply adding a base wouldn't work has to do with bee venom being water-soluble. Since humans are composed of high quantities of water, the venom quickly disperses once you are stung. This means that when you add a base to the surface of the skin, very little would actually be able to neutralize the acid. While the acid isn't doing that much damage, the other components do each play a role in how the venom affects your body. Here we will just speak about melittin, because that is the main component aside from water.
The main source of pain and redness in a bee sting is the breakdown of the phospholipid bilayer or plasma membrane of your red blood cells. The bilayer has a structure similar to that of soap with a polar or ionic head and a hydrophobic chain of nonpolar CH bonds. For a phospholipid bilayer, you have an ammonia group and a phosphate group, so there is both a positive and negative charge on the head, causing many species to be attracted to that surface. On the other hand, the inside of the phospholipid bilayer is nonpolar and attracted to itself opposed to other ions.
So the way melittin actually damages your red blood cells is still widely debated. There's a few different theories bouncing around, but the one that's the most accepted is the detergent-like model. You can use melittin to form stable pores within cell membranes. This type of cell membrane breakdown is generally what happens when melittin is used for medicinal purposes. This is stable because while some of the fluid in the cell leaks out due to pores, it is not enough for the cell to actually collapse, and it's able to remain in equilibrium with its surroundings. These are the two different types of pores you can form. Peptide molecules are represented here as red rectangles, and the phospholipid bilayer is represented by a dark gray circle, which is a hydrophilic head group, and the wavy lines are representative of the hydrophobic hydrocarbon change within the membrane. The top image, labeled A, is called a barrel stave pore. In the barrel stave model, the membrane will form bundles which hydrophobic surfaces interact with the lipid core of the membrane, while the hydrophilic surfaces point towards the forming pore. In the bottom image, labeled B, it is called a toroidal pore. In this case, it begins to form almost like half a micelle. The chemistry here is quite similar to that of how soaps form membranes. The hydrophilic ends of the membrane is attracted to itself, and as are the hydrophobic regions of the membrane. This causes the hydrophilic ends to move towards each other, forming a hydrophilic outside that interacts with the hydrophilic areas of the peptide, so the pore is lined by both the lipid head groups and the peptide molecules. What you're seeing here is what you would expect to see at the sting site where melittin is attacking the phospholipid bilayer of one's red blood cells. In this case, there's a high concentration of melittin, and it begins to follow the detergent-like model. So, in the top image, you can see that the melittin is just sitting on top of the phospholipid bilayer and not really affecting the structure or orientation of the membrane at all. This only occurs at a low concentration. As the peptide concentration increases, it causes aggregation of the peptide molecules and thinning of the membrane, which is what you see happening in the middle image. In the bottom image, the concentration of melittin has exceeded that certain threshold where the membrane begins to disintegrate into micelles. This occurs, again, for the same reason that soap forms micelles when in solution. Your body has a lot of water in it, which is attracted to the ionic head of the membrane, while the hydrophobic areas want nothing to do with that water. As such, it is more stable for it to form a sphere with a hydrophilic outside that's interacting with the water in your body and the ionic regions of the melittin, while the hydrophobic region of the membrane is just interacting with itself and the hydrophobic region of the melittin. The reason that this can happen with melittin in particular is that the hydrophobic region of the melittin is attracted to the hydrophobic region of the membrane, which causes it to be pulled down into the membrane, which is why you see that membrane beginning to thin out. The hydrophobic region is pushing down on that membrane as it tries to get closer to the hydrophobic region of the membrane. The reason the hydrophobic region of the melittin can interact with the hydrophilic area in order to get closer to the inside hydrocarbon change is because of the electrostatic attraction of the positively charged areas of the melittin and the negatively charged oxygen in the phosphate group of the phospholipid bilayer. So, the ionic regions are interacting favorably while the nonpolar region of the melittin pushes more and more on the membrane trying to get to the hydrocarbon inside of the phospholipid bilayer, which eventually causes the membrane to break up and form micelles. This is referred to as the detergent-like model because it cleans away the membrane entirely from a given cell.
The use of bee venom can be traced to ancient times when Hippocrates, an ancient Greek physician known as the father of medicine, used bee venom to treat arthritis and joint pain. Back then, the bee venom was directly administered using the bee's stinger. The live bee was held with tweezers and placed on the part of the body to be treated, at which time the bee reflexively stings. Today, this method can still be used or it can be given via syringe. Since the time of Hippocrates, interest in the therapeutic value of bee venom has grown. While a randomized trial did not show effectiveness in the treatment of multiple sclerosis, a review of studies found affirmation in arthritis treatment. This is due to the cortisol release that the venom stimulates. A 2005 Oxford University study found that patients experienced positive side effects on painful, swollen joints when the bee venom was used in the acupuncture treatment of arthritis. Melittin is currently being analyzed for the treatment of several cancers such as renal, lung, liver, prostate, bladder, and leukemia. Researchers at University of Illinois have successfully separated proteins and peptides from bee venom and used melittin to block tumor growth. Scientists have been working to modify the melittin molecule to attach a cancer-specific antibody that will only destroy the cancer cells, leaving healthy cells unharmed. This method would prevent the undesirable side effects such as vomiting and hair loss linked with chemotherapy. Studies on melittin have shown nanoparticles containing bee venom can destroy human immunodeficiency virus, HIV. It does this by poking holes in the protective casing surrounding the virus, while protective bumpers prevent interaction with healthy cells. In addition to treatment of already infected patients, a gel is being developed using bee venom to prevent the spread of HIV. It may even have the ability to be used as a contraceptive. Melittin has a large potential for drug therapies beyond HIV, such as hepatitis B and C. In addition, there are numerous conditions bee venom has been used to treat, such as chronic injuries like tendinitis, hay fever, removal of scar tissue, gout, shingles, and burns. However, all of these studies are still being completed, which may call into question their credibility. Because of the lack of long-term evidence proving its medicinal value, this therapy should always be used in addition to other treatments. These busy little bees work hard to pollinate our plants, serving an incredibly important role in our world. However, equally as important are the roles that bee venom can fill in modern medicine. To overview, the main component in bee venom is melton, which gives the venom its cell-degenerative properties, thus allowing it to be used in many treatments today. This multifunctionality of bee venom shows just how important bees are in our world.